transitivity and mixed properties for expanding Laurent maps on the.
Okay, thank you very much. At first, I'd like to thank the organizers for organizing this conference and the possibility to give the talk, which was not easy in this time. Okay, so let me start. Okay, so mainly the results presented in this talk were obtained together with Piotr Brocha and Paweł Potorski from Krakow. Some results were obtained together with Angela Berger, or at the time she was called Stachelberger. So let us consider a continuous strictly increasing function f from the interval 0,1 to the interval 0,2, which is differentiable on the open interval without a finite set. And the infimum of f prime is the infimum of all points where f is differentiable. And we suppose that the infimum of f prime is larger than 1. Because of these assumptions, there is a unique C such that f of C is 1. And now we define the f of x, fx modulo 1, which is the same as fx minus the lower Gauss bracket of f of x, the largest integer smaller or equal to f of x. And such a map is called an expanding Lorenz map. It is a piecewise monotone map, but it has a discontinuity at C. We have the limit of dfx to C from the left is 1, and to C from the right is 0. Okay. So this map is not a topological dynamical system in the usual sense, because you need a compact matrix space and a continuous map of it. And here the map is not continuous, but you can do a standard doubling points construction, and therefore you can apply all standard definitions of dynamical systems, of topological dynamical systems. Okay, yes, I suppose all of you know what is topological transitivity. There are several possibilities. For example, you can say there exists an x such that the omega limit of x is the full set 0, 1, or equivalent for every non-empty open u and v. There exists an n such that df at n u intersecting with v is non-empty. And then we obtain the following result for expanding Lorenz maps with infimum f prime is at least the third root of 2. So set better the infimum of f prime and suppose that one of the following properties is satisfied. So beta is at least the square root of 2, or in 2 and 3, beta is at least the third root of 2, and at first f of 0 is at least 1 over beta plus 1, and the third is the equivalent from the other side. F of 1 is at most 2 minus 1 over beta plus 1. And in all these cases, the map df is topologically transitive. So let's consider the map df, whose graph is shown in this picture. And here we have that beta, the infimum of f prime, is 13 over 10, which is larger than the third root of 2. But we have f of 0 is smaller than 1 over beta plus 1. And because the Brown set in this figure is invariant, the map is not topologically transitive. because you can never reach a set in the non-Brown set from the Brown set. Any steps. And let me, for example, show what happens to the third interval. The third interval is mapped to the second interval. The second interval, there are two possibilities. It is mapped to the first interval and to the first interval. Okay. So, and similar, if you have the map fx 8/7 times x plus 3/5, which is shown in this figure, we have this beta is smaller than the third root of 2. And again, the Brown set shown in this figure is invariant, and therefore the map is not transitive. Okay, and if for every non-open U and V, there exists an N, a large N, such that df small n U intersected with V is not empty for all small n, at least large N, then the map df is called topologically mixing. Obviously, this implies topological transitivity. And because of our next result, we see that in the situation of theorem 1, there are only 3 cases where the map is not topologically mixing. So again, set beta the infimum of f prime, and suppose that one of the following properties is satisfied. They are more or less equivalent to the conditions 1, 2, 3 as before, but always with exactly one exception. In the first case, this is the map should not be f equal the square root of 2 times x plus 1 minus 1 over the square root of 2. Here you see the other exceptions. And I think I will show now the counterexample in 2. So the map third root or 2 times x plus this expression. Yes, exactly. So, yes, this map is topologically transitive by theorem 1, but it is not mixing, because if you start in the in the one of the blue intervals, you get to the yellow interval. What I did right, orange interval. So, okay. If you are in the orange interval, you get to the brown interval. And from the brown interval, you get to the blue interval. And therefore, for example, you cannot come in from a blue interval in n steps to the brown, to some subinterval of the brown interval, if n is if 3 divides n. So you see it cannot be topologically mixing. Okay. Yes, and now using theorem 1 and theorem 2, we can draw the region of beta and alpha with beta between the third root of 2 and 2, and such that infimum of f prime is at least beta and f0 is at least alpha, implies that df is topologically transitive. So we know in the orange region this is true. In the pink region, it is not true. And in the white region, it's open. So I do not know it. Okay, and you see these 2 violet points. These are the points where the map is transitive but not mixing. So if you, yes, better results you can obtain if you consider maps of the form fx beta x plus alpha, so the linear case. And in this case, you have that the map is topologically transitive if and only if beta is at least the square root of 2, or beta is between the third root of 2 and the square root of 2, and alpha is between 0 and less than 1 over beta squared plus beta. And similar in the third case, which is and moreover, the map DF is topologically mixing if and only if this is satisfied, except for the three exceptions we had before. So, and now in this case, it's much easier to draw the region where we have transitivity. This is the orange region again. In the pink region, it's not transitive, and the violet points are these points where it's transitive but not mixing. Okay. So generalizing these results leads to the notion of NK cycles. This concept was introduced by Balmer in 1979. I think it was a thesis at the University of Warwick, and Piotr Brocha looked at this thesis so that we could work with it. So, and this notion is if Z0 to Zn minus 1 is a periodic orbit of period n, and these are ordered in exactly this way as described above. And it is called an NK cycle if, this is an NK cycle. And such an NK cycle is called primary NK cycle if df of Zj is Zj plus k modulo n. So you know how it goes further. K and n are co-prime. Zk minus 1 is at most df of 0, and Zk is at least df of 1. Yes, and Paul Glendinning claimed in 1990 that an expanding Lorenz map with a primary NK cycle cannot be topologically transitive. Unfortunately, this is not true, or also it is almost true. There are only a few counterexamples, and we have seen such a counterexample before. It is exactly the example we had before. And you can find that Z0, Z1, Z2, where Z0 is df squared of 0, Z1 is df of 0, and Z2 is df at 3 of 0 is a primary 3-2 cycle. And this map was topologically transitive, but not mixing. So, and the correct result is if df is an expanding Lorenz map with a primary NK cycle, and if df of 0 equals Zk minus 1 and df of 1 equals Zk, then the map is topologically transitive but not mixing. And if df of 0 is larger than Zk minus 1, or if df of 1 is smaller than Zk, then the map is not topologically transitive. So you can now draw a new picture here with the pink regions. These are the primary N1 cycles and primary N minus 1 cycles, at least up to a certain level. Otherwise, I would not see very much where it is not transitive, and the points where it is transitive but not mixing. And again, the orange region was the region we had before. Okay. So now I come to the definition of locally eventually onto given by Paul Glendining in 1990. Be careful, it is different from the notion of locally eventually onto given by Vienna just before. And I have to say, I would expect locally eventually onto as in the definition of Vienna, not this one, but it was the definition of Glendining. So, and according to Glendining, map DF is called locally eventually onto if for every non-empty open U, there exist open intervals U1, U2 in U and natural numbers N1 and 2 such that DF at N1 maps U one homomorphically to 0C, so the left part of the voice of monotonicity, and TF and at N2 maps U2 homomorphically to C1. Yes, and this notion implies that the map is locally eventually onto in the usual way as Janne defined it. Yeah. Yeah. So it yes. It's a kind of stronger. Yes. Yeah. Yes. Okay. But another notion is such a Lorenz map DF is called renormalizable if there are numbers U1 and U2, so such that C is between U1 and U2, and natural numbers L and R with at least L plus R is at least 3, such that DF at L is continuous on U1C, DF at R is continuous on C U2. The limit from X X to C from the left of DFL of X equals U2, and the limit to from the right of DFR of X is U1. And because of some exceptional cases, DF is said to be special trivially renormalizable if DF0 is 0, or DF1 is 1, or DF0 is C, or DF1 is C. However, observe that a special trivial renormalizable Lorenz map need not be renormalizable. Okay, yes, I just mentioned that every locally eventually onto Lorenz map is topologically mixing. And it was widely believed that in the case it is not special trivial renormalizable, the F is locally eventually onto if and only if it is not renormalizable. Unfortunately, this is not true. And to give a counterexample, choose beta as the largest zero of the polynomial x at 4 minus x minus 1. Define alpha 1 minus 1 over beta and set fx beta x plus alpha. Then we get c is 1 over beta squared, and here you have some digit of this number. And furthermore, it is important to note df3 of 0 equals df at 2 of 1 and equals c. Okay, df of 2 at 1 is meant as the left-sided limit of 1 or df squared. Okay, so Here you have shown the graph of the map, and you see these brown intervals, and you will see a bit later that this brown interval is mapped to this left 0C in 12 steps. So by df at 12 homomorphically. And therefore the map is locally eventually onto. This can be used to prove it's locally eventually onto. But it is renormalizable. If you take U1 df squared of 0, U2 1, L equal 4, and R equal 3, you see here the left part is df at 4. And at the right part df at 3, so you see this renormalization. Okay. Now I have an animation. What you will see that this interval is mapped to, I hope it starts, yes. So we have the third iteration. What you now then will see at the second iteration, it splits up. So df at 2 is not a homomorphism. But you see it in the 12 steps, it is glued together at exactly the right point, so that df at 12 is. So we have here the third iteration. Fourth iteration. Five. Six. Seventh iteration. Eight. Step 9. Tenth iteration. Eleventh iteration. Now the 12th one, you see it is glued together exactly at the right point. To make the F12 doing. Okay, so you have seen this map is locally eventually onto in the definition of Glentinning. So, but you can improve this definition of Glentinning if you call a map strongly locally eventually onto, also in the sense of Glentinning, if additionally to the original definition, you require that df squared and up to df at n1 are continuous in u1, and df squared up to df n2 are continuous on u2. So, that exactly what happened here cannot happen. And with this, we have the following theorem. For Lorenz maps, the following conditions are equivalent. The map df is strongly locally eventually onto in the sense of cantining. And second, the map df is not renormalizable, or it is special trivial renormalizable. Okay, and essentially this is all. Thank you very much. Dziękuję bardzo. Just one moment. Velikše, štějego, najlepšego, zkazí obecin.
Okay, are there any questions? Comments?
I think there was an online question. Okay.
Okay.
Precisely related. You considered here this Leo, locally eventual onto, somehow related to mixing.
Yes.
But in my paper with Juan Rivera Letelier, we introduced something weaker, like that there exists such n, capital N, that for every open interval, after some sufficiently high iterate, its images from time, let's say time k, k plus 1, k plus capital N, that this finite number of intervals covers everything.
Yes, yes.
So we introduced this notion suspecting that it is well known, but we didn't know, so we just put it. So do you know, or maybe somebody else knows where something like this is considered? So we don't need that image of small interval covers everything, but in a
I know,
bounded a priori number of steps covers everything. I don't know.
I have seen it in some papers, of course, in yours,
we have
but
it in our memoir, but we didn't make an effort to look for in the literature. We just needed it ad hoc.
I do not remember exactly where I have found it. Yeah. Yes.
That's what I need, and again, it fits not to mixing, but fits to transitivity. This word, so. Okay, we of course had in mind spectral decomposition. After a finite number of steps, it covers everything.
Okay, I have also a question. So how about, for example, for this beta x plus alpha examples, how about specification? Have you? Because like if it were continuous, then mixing is equivalent to specification. But what happens when you have this kind of discontinuous maps?
I do not remember it exactly, but there is a paper of Franz Hofbauer where I consider this. And I can look if I find it, but now I do not know it exactly what were the results.
Okay. Are there any more questions? If not, then let us thank the speaker again.